So, in the OSI model what we studied about is the data link layer and the MAC layer and their related protocols for the data communication part or their services. Coming to the next of the next layer in the OSI model, you have the network layer. What is the function of the network layer? Why the network layer is required? When the data link layer does the framing part, then sending the frames in sequence to the receiver and doing all the job of the frame control, flow control and the error control part, what the network layer does? We know that the main objective of computer networks is the transmission of the data or the packets. That means, if there is a sender and there is a receiver, the ultimate goal is the packet has to reach from the sender till the receiver. Now, because we know about the network little bit, we can see that the sender and the receiver, they can be present in a same network, or it may happen that the sender is in a one network and the receiver is in another network. Like if I say the sender is in NIT Rourkela network, then the receiver can be in the NIT Kurukshetra network. Now, how this sender and the receiver are identified in the globe and the packet is delivered to the receiver. That is what is the job of your network layer. That means the network layer is responsible for the end-to-end delivery of the packet. When I say end-to-end, I mean the host to host. That means the job of the network layer is to identify a host in the globe and deliver the packet or the data to him. That is what is the job of the network layer. So, what we studied with this network layer is, we assume that an entity or a node is present in a geographical location, we say a subnet. If the whole globe is a network, we assume that your sender is in one subnet and the receiver can be in the same subnet or it can be in another subnet. So, finding the path between the sender to receiver is the job of the network layer, and this path finding is also called route the packet to its destination. So, routing is the objective of your network layer. Any packet that is generated at the sender side, when it comes from the application layer all through the transport layer and the presentation layer, session layer, everything, then coming to the network layer what it does, it finds the path in the globe or it identifies the destination or the receiver in the globe and delivers a packet to the receiver. So, it is a communication or it is a peer-to-peer communication between the sender and the receiver in the network layer, or what we say routing the packet from the sender to the receiver. So, like every other layer, the network layer also provides the service to its upper layer, because that is the job of every layer in the OSI model. Now, the first function or first service of the network layer is, it provides the service to the upper layer, and who is the upper layer? The transport layer. Now, when we say about the provides the service, what kind of services it can provide? The network layer can provide a connection oriented service or a connection less service. You think of a telephone line. A group of people, those who are communicating over the telephone line, right? What they do? How do they do the communication? If there is a sender side, there is a receiver side, then what this telephone group what they do, they establish a connection between the sender and the receiver. They do the communication between the two ends, and once it is over, they terminate the connection. The data is delivered. So, this is a kind of one way of communicating which is called the connection oriented service, and this is a reliable service. or what we say in terms of routing, we say this is a circuit switching service. A dedicated connection between the two ends, data communication and the termination, 3 stages. The other group, the connection less group, they work similar to your telegram. When you do the telegram, you do not know which path your data or the message will follow. You send the data or you deliver the data in the post office. Now, the post office decides through which route it will follow, or it will forward the packet or your data, and ultimately it reaches to the destination. There is no dedicated path between the sender and the receiver, but in every link or every path, the current sender or the current node identifies who is my next neighbor, or what we say the next hop, who can handle my data, or who can receive my data and forward further. So, that is what is another kind of service, or what we say connection less or the packet switching. During this service or during this kind of communication, the sender provides the complete address of the receiver and waits till the receiver receives the packet. He does not even know which path my packet or my data is going to follow, but his job is only to send the data or to send the detailed address of the receiver to the router or the path, and it can follow that. That is what is your packet switching. Now, with these two kind of services, connection less and connection oriented, OSI model supports both of these services in the network layer. So, how the path is established or the packet is routed between the sender and the receiver. It may happen that the receiver is an immediate neighbor of the sender. That means it is the next hop of the sender. So, the communication is a one hop communication. It may happen that the receiver is somewhere here, and in between there are multiple nodes who are storing the packet and forwarding to the next hop, again storing the packet, again forwarding to the next hop till it reaches the receiver. This is what is called multi-path communication or multi-hop communication, you can say. So, either the routing could be single hop routing or it could be a multi-hop routing. So, who decides it? How this number of hops are decided? Definitely there is an algorithm who decides the path to route the packet from the source to the destination, and these algorithms are called the routing algorithms. Who decides who is my best hop or my immediate hop who can help me in forwarding my packet to the receiver or the destination. That is what is the job of any routing algorithm. So, because the routing algorithm has to decide the path or the best path, you can say, for sending the packet, these routing algorithms are again classified into two types. One is non-adaptive and another is adaptive. When it comes to the non-adaptive kind of routing algorithm, let us say you have a subnet or a topology like this, and any node can be a sender or any node can be a receiver in this subnet or in this topology. So, what the non-adaptive kind of routing algorithm does, it finds the best path, or you can say the optimum path between any pair of nodes, assuming them to be the sender and the receiver. And this path is stored, and whenever the router comes up, the path or the information is downloaded to the router, saying that if you want to communicate with any of the nodes in the subnet, you have to follow this path. That means it is a proactive kind of routing algorithm, giving the prior information to any router who comes up, saying that if you want to send to any node in the subnet, you have to follow this path. So, it is a non-adaptive or a static routing algorithm. Why static? It does not consider any of the network scenario. What are the network scenario? The traffic, the delay, the cost associated with it, or the noise, anything, there it can have any of these parameters associated with it. But the static routing algorithm does not consider the current scenario. Whatever is pre-decided, that is given to the router and the router has to follow that path. That is why this is called a non-adaptive or static routing algorithm. Coming to the adaptive kind of routing algorithm, if at one point of time this is the sender and this is the receiver, the route was decided to be via this node, let us say node X, in the next moment it may happen that this node or this route is heavily loaded or noisy, the node can now find this route as its current route for reaching to the same receiver. That means it dynamically changes with the network scenario and the topology. So, this is a dynamic kind of routing algorithm. So, some networks or some subnets, they allow the static network routing algorithms, whereas some other they allow the dynamic routing algorithm. So, we will first see some of the static routing algorithms or the non-adaptive kind of routing algorithms. But before that, we must understand there is a principle called principle of optimality in the routing path. What it say? If I is a node and j is another node in the subnet, and if there exists a path between I and j which is assumed to be an optimal path, when you say the path is optimal, you do not have any better path than this. In every respect, this has proved to be the best path. Let us say I and j, this is the path which is considered as an optimal path. Then any node that comes in between this optimal path will have the same route as the optimal. That means, if z is another node here and if the route has to be established between this z and j, then definitely this will be the optimal path again. You cannot have any other alternate path if there exists an optimal path already on the same route. That is what is the principle of optimality, and with that principle we will go for the different routing algorithms, right. So, coming to the non-adaptive or the static routing algorithm, one of the very popular routing algorithm is the shortest path routing algorithm, or this is also called Dijkstra's algorithm. What this algorithm says, if there exist any multiple paths between a sender and a receiver, then the shortest path algorithm finds the optimal or the shortest path in terms of geographical location or number of hops or any other point to be considered, and it gives you the best path which is the shortest one. If you consider the number of hops as the parameter, let us say A is a node. If you consider number of hops as the parameter, then I can say the length of A, B, C is same as equal to length of A, B, D. Do you agree? Because number of hops is the parameter. So, how many hops? 1, 2, here also 1, 2. So, both are having 2 hops. But if you go for the geographical distance between the nodes, then I cannot say these two are having the same length. So, in this algorithm we assume that the distance between two nodes is not the number of hops, rather some other weightage like maybe a distance, maybe your noise or any other parameter related to the the networks. So, now let us assume in topology we have a subnet like this. If I have a network topology like this with 8 nodes A, B, C and let us say A, B, C, D, E, F, G and H. So, in this topology I have 8 nodes and the vertices of this graph, they indicate the nodes with the links or the connectors, they indicate the connection between the nodes, and every link has its weightage, and these weightages are considered to be the geographical locations between the two nodes. So, if I have a topology like this with the weightage of this, let us say 2, 6, 2, 1, then 7, let us say 3, this be 3, this be 2, this be 2, then let it be 2 and 4. So, I have a topology like this with 8 nodes and the links, and every link has got its own weightage. Now, my objective is to find the shortest path between the source, which is equal to A, and the destination, which is equal to D. So, initially every node knows that there is no path or no route to the destination. So, what they do, they link there or they give their nodes with a weightage of infinitive, saying that I do not have any path for the destination. So, that means this is something I say I do not have any path, no path is yet decided. So, they give an infinity path, means undecided path between these two. Only this node has the information. So, if I start with this, rest all the nodes are having the same information, like this from B, this is from infinitive. Let it be the, I give a value not known to anybody. So, the values are not known to anybody, infinitive and not known. This is also infinitive and not known. This is also not known, right. Now, we will find out which path is there, starting with my source, that is A, and I say A as my working node. Currently, I am working with this node A. So, now I start with A. Who are the adjacent nodes to A? One is B, another is G. Now, my path from A to B is already known to me, that is 2, and A to G is known to me, that is 6. Now, once these paths are decided, now B knows that my current weightage is 2. So, infinitive will be replaced with a new value. New value means it should be lesser than the current one. So, definitely 2 is lesser than infinitive. So, I find a shortest path from A. So, I say 2, A. That means I have a shorter path from A to B, which value is equal to 2, right. Similarly, G also understands that earlier it was infinity with no value. Now, it realizes that I have a shorter path from A to G, or a calculated path which is equal to 6 from A. Now, so values are now known, two values are known to us in the whole of the network topology. One is 2, another is 6. Now, tell me which one will be a shorter path if I start from A. As per the algorithm, the packet should follow the path between A to B or A to G. Definitely a smaller weightage or a lesser value, which is equal to B. So, my next working node is B. The packet comes to B. So, B is the next working node, because this is the shortest value or the lowest value among the whole topology. Now, coming to this node B, you check for all the adjacent nodes of node B. One is E, another is C. So, what is the distance between B to E? That was 2, right. So, now if 2 is already there and another 2 means this value will be how much? Cost will be 4 and path will be B. So, that means if the packet follows this route to reach E, the cost will be 4 and the path followed is B, correct. Similarly, if the next adjacent node is, if it goes to C, then the path followed is 2 followed by the 7, which is equal to 9, then B. This is the new value now, and 9 is definitely less than the infinitive. So, I can replace 9 now, right. So, now in the topology, whole of this topology, other than these two working nodes which have already been visited, tell me which one is the having the least value. Definitely node E, having the least value of 4, because other two are, one is 9, another is 6, others are the infinitive. So, a node having the least value or the shortest path you can say is node E. So, now node E becomes my next working node. So, E is the next working node. If I draw this again to make it more clear, now my topology or the subnet is like this. A and B is now 2, A, this one is now 6, A, this is now C, and this is G, and this is E, which is equal to 4, B, and this is equal to again C, D, F and H. So, now my next working node is E as decided. I will check for the adjacent nodes of E. So, who are the adjacent nodes of E? One is F, another is G. Now, what is the distance for E to G? Is 5, 1, right. So, if this is 4 plus 1 will be 5 now. Can I replace 6 with 5? Because I have a better value than 6 now. So, now the new value is 5 and E. E is the current path now. And this one will be, F will be equal to, earlier it was distance is 2, the cost is 2. So, 4 plus 2 is, this is 6 E, and this one is 9 B as decided earlier, right. Now, you tell me in the topology who is having a better value, the 5 E or 6 E or 9 B? Definitely it is the 5 E having the least cost. So, my next working node is G. So, G becomes my next working node. Coming to G now, find out who are the adjacent nodes in this. The next adjacent node is H and E again. E is already visited, so we do not have to go there. H is the next adjacent node. So, the cost to G to H is 4. So, now this becomes 5 plus 4 is 9 and then G, right. So, there is no other value now. So, I have 3 values now, C at F and another at H. Who is having the least cost in this scenario? Definitely F, because he is having the least cost or equal to 6. So, my next working node is F. So, F is the next working node, correct. Now, coming to F now, who are the adjacent nodes? One is C, another is H, and the cost from F to C is 3. So, 6 plus 3 is 9 and this value is already there. That means to reach at C, either it can follow the path B or it can follow the path 9F. In both way it is possible. So, either you replace it or you do not replace, does not matter. The next one is from F to H, what is the value? 2. So, 6 plus 2, which is equal to 8, and 8 is definitely less than 9. So, I will replace this value with F. Let us say we are not replacing this one, I am replacing 8. So, out of these two values 9 and 8, who is the having the least value or the shortest path? Definitely this one. So, my next working node is H with the value 8. Now, coming to this, the adjacent node of H is now D. So, if I go there, 8 H to D, the cost is 2. So, definitely 8 plus 2 is now 10 and H, right. Now, check for the node C and D. Who is having the lowest value? Definitely C. So, my next working node is C. And 9, from C to D the cost is 3. So, 9 plus 3 is 12. Can I replace this 10? I cannot, right. That means now D, when it comes to D, this is the only node left. So, the next node is D is the working node and D is also the destination. So, now which value D is carrying? A value of 10 with the path of H, correct. So, now I reached, or the algorithm has reached to visited all the nodes and assigning the working nodes among all, and finally it reached to the destination having a total distance cost of 10 through the path of H. Now, you backtrack from D to H. If you backtrack from D and the preferred path was H, so when you go to D to H now. In H, what is the preferred path? 8, and the preferred path was F, because at this point this was having the best value. So, the next was from H to it was, so from here you are coming to H, and from H you are going to F. So, the next value was F. At F you find that who is the preferred path, that means through which node I got the least value, the E. So, my next node is E, which has to be followed. When it comes to E, it finds that E is having a better value when it follows the path B. So, from E it goes to B. When it goes to B, it says that B got a least cost when it was forwarded by the data from node A. So, it goes to A then, and finally A is the sender itself. That means the route that is established between A to D was A, B, E, F, H and D. So, you got the better value. In the original figure you check, A to B is 2, then B to E is 3, 2 plus 3 is 5, then E to F is 2, 2 plus 3 plus 5 plus 2 is 7, then to H 7 plus 2 is 7 plus 2 plus, sorry, 2 plus 3 is 5 plus 2 is 7 plus 2, 9 plus 2 is 11. How come we got 10? Oh, here it is 11, right? H, after H we had the C was the better path. H to D was, here it is 8. Then we did something, there is some mistake. H, F, B to E is, oh, this is 2. Are you sure? Okay. Okay. So, in the original subnet graph, 2 plus 2 is 4, plus 2 is 6, plus 2 is 8, plus 2 is 10. So, the total shortest path is 10 and the path followed was this. This is what is your shortest path algorithm, which is a static routing algorithm, and it decides that whenever there is a packet to be sent from A to D, this is the path to be followed. So, it becomes a non-adaptive path, or it cannot be changed, and the cost remains always 10. That is what is your shortest path or the Dijkstra's algorithm, and this shortest path still now even in the wireless network routing also, this is any routing protocol is also a modification of this. This is the basic of any routing protocol till date, maybe for a wired network or for a wireless network. This is what is your Dijkstra's algorithm or the shortest path algorithm for the routing of the networks.